Our goal with this video is to discuss the graphical interpretation of instantaneous rate of change. Today in class we talked about average rate of change, and you saw a video on that and calculating average rate of change. So today we're going to talk about something new. It's called instantaneous rate of change, which is kind of like when you're driving in your car and you see the speedometer and it's telling you exactly how fast you're going at that particular instant. So the number you're seeing, like it says you're traveling at 110 kilometers per hour, that is not an average rate of change. That's your instantaneous speed. That's your instantaneous rate of change. That's exactly how you're going at that particular moment. So what our goal here is to look at how to interpret that, graphically, and also how to calculate that. Okay, so we talked about this slide yesterday where we could have a curve, and when we drew the rate of change changes as the curve changes, and we talked about finding the average rate of change between 2 points. We would draw, graphically, we draw a secant line between those 2 points. Algebraically, to calculate the average rate of change, we found the slope of that secant line using the 2 points. Now, to find instantaneous rate of change would be like after, say, 2 seconds, I want to know exactly how fast I'm going. Whereas that average rate of change says, well, between 1 second and 4 seconds, we are going on average this speed or this rate. So our instantaneous rate of change is drawn at one particular instant. So we represent that with a tangent line. That tangent line comes down and crosses at that one particular instant. In this case at 3, when x is 3, that's the tangent line crossing at 3. Notice the tangent line comes down and touches a curve at one little localized spot. Okay, so it doesn't pass through. So for example, this is not a tangent line. It doesn't pass through a curve. It touches a curve and scoots off the other side. Okay. So we use the tangent line because we're looking at one particular moment, one particular instant. We need 1 point. We would draw that tangent line. The slope of that tangent line is, say, the rate of change at that particular moment. That's our graphical interpretation of instantaneous rate of change. So say I had to calculate the instantaneous rate of change at that moment, at x equal to 3. If I had a nice perfect graph and I've drawn a tangent line as accurately as we can, which sometimes is unreliable, if this was possible, we had a tangent line on a graph, then all we would need to do is calculate the slope of that tangent line, which is done our normal way. The slope of any line is the rise over the run, or the y2 minus y1 over x2 minus x1, or that other one that we've been talking about, f of x2, which is really the y2, which is really the y1 over x2 minus x1. So either or is fine. But so if I had to calculate the slope of that tangent line, I still need 2 points, okay? Because we can't calculate slope other than that formula, which needs 2 points. Now, since I'm going to pass through this point here, that's the point 3, 3. That could be one of my points, and all I need, since it's drawn, this is already drawn on here, I just have to pick a point off the tangent line. Let's say I pick that one right up there on that point, which is the point 2, 5. So knowing those 2 points, I can now calculate the slope of that tangent line, which then is going to act as my estimate for the instantaneous rate of change. Okay, so find the slope between these 2 points. I already have the y values. So I'll call this point 1. This one's 0.2, so then I have y2, which is 3, minus y1, which is 5, all over 3 minus 2. So the slope of this tangent line is 3 minus 5. This is minus 2 over 1, which is minus 2. So the instantaneous rate of change at that particular moment, at 3, is a negative 2. That is if we had a tangent line drawn. Now, most times we can't draw a tangent line nicely like that, and you can't also rely on that because of our human error. We'll put a ruler on there, and it won't be that great, and the graph might be drawn wrong. So we have a slightly different approach, and we're still going to look at the graphical interpretation of that approach. Okay, so say I have this function here, which is a cubic polynomial in red, and I've drawn a secant line between when x is 10 and when x is 15. So right now the slope of this line is written right here, over here. It's 1.6. The slope of that line represents the average rate of change between 10 and 15. Well, say I wanted to know the instantaneous rate of change at 10. At that point right there, I wanted to know the instantaneous rate of change. Right, which means I would draw, if the instantaneous rate of change is represented by that slope of a tangent line. Now watch my mouse, because I'm going to try to draw the tangent line or just trace it on here with my mouse. Okay, so remember, I don't pass through the point at that point. Like, not straight up and down is not a tangent line, or straight across isn't a tangent line. It's kind of got to come in and touch and come back out. Okay, and it's got to just touch. Now notice I can't draw it on this side because I don't skim across it. I kind of hit over here and I hit over here, so it's got to be drawn on the outside of this kind of bend. So watch my mouse here. Here it comes. So if I'm going to draw one line that touches that point and goes away, then I'm going to come in this way, come in, and then touch, and then go back out. Okay, so this is what my line should look like. Now look at the purple line. That does not look like my line. It does not use the slope of that line. Or is not the same as the slope of the line I'm tracing right now with my mouse. It's got a different slope. So right now that purple line is not a great estimate of using of the tangent line at that particular point. And if you think about it, I can't calculate the slope of a line when I only have 1 point. I need 2 points to calculate the slope of a line. And if I'm not going to draw it because of accuracy problems, the approach is this. Say if I want to leave this point at 10, because I want the slope of the tangent line at 10, watch what happens when I drag this point a little closer. If I drag it a little closer, notice what happens to the purple line, that secant line. It got, if you noticed, a little closer to the shape of what the tangent line is going to look like. Remember, the tangent line is coming in here, touch it, and going right back out. Coming in here, touch, and going right back out. So now if I go a little closer, I'm getting closer to that look. I'm coming in here, touching, and coming right back out. And as I get closer and closer, notice the slope of that secant line is getting closer to what the slope of the tangent line would be. So I'm coming in here and scooting and coming right and shooting right back out. Notice that purple line is getting close to that. Getting close, getting close. Now I'm going to get real close. It would come in here and touch and come right back out. If I get it real close, that's a pretty good estimate for the slope of the tangent line. Pretty good, right there. Now if I'm right on top of that point, look what happens to my slope. It's undefined. Right? I can't calculate a slope if I'm using the exact same point. That's because, think about the denominator in the slope formula. It's x2 minus x1. Both x's are the same. So you're dividing by 0. You have a 0 in the denominator. It can't happen. So we need 2 points to do slope. So what we do is we get really close. If you can find a point really close, then you can use those 2 points to estimate the slope of the tangent line, which is the average rate of change. And that's our theory. We'll get really close to estimate the slope of the tangent line, or the average rate of change. And that's all we can do. So let's go back. I've got a note here for you informally. It looks like this. So we've got the relationship between the slope of secants and the slope of tangent lines. Let's say I have point Q, which is maybe like that point that was at 15 to begin with, and it becomes very close to the tangent at point P, where point P was like where I was at 10. Then the slope of the secant line gets closer and closer and closer to the slope of the tangent line, and therefore we can use that slope of the secant line to estimate the slope of the tangent line. Okay, so that's our graphical interpretation of getting a slope of a tangent line, or estimating the instantaneous rate of change. I'm going to calculate one in the next video. So watch the next video where I'm going to do an algebraic interpretation of that, which is if I have the function equation, I'll be able to calculate it by picking points very close together.